teacher series on soil mechanics. Yesterday we have given solutions and numerical problems. Along with the numerical problems, solutions are also provided. So in this today's class we are going to discuss the remaining concepts that are very important for GATE and IES. Because if we go on keep on discussing what is important for exam, that only we discuss. Remaining aspects we will not touch. Only those which are asked frequently in competitive examinations. Such topics we give more weightage, more time. We spend more time on such concepts which are being asked in all the competitive examinations such as GATE and IES. Other topics we give according to the time. We give weightage according to the time. Today's class we are going to discuss the differences between coarse grained soils and fine grained soils. Coarse grained soils and fine grained soils. From our first lecture onwards, we will keep on discussing that coarse grained soils are formed from the physical weathering. From the physical weathering, coarse grained soils are formed, and fine grained soils are formed from the chemical weathering. That's why fine grained soils have plasticity characteristics due to the electrochemical forces. Due to the electrochemical environment they are formed. And also, here one important point to be noted in case of fine grained soils. Note, for fine grained soils, specific surface area is high. Specific surface area is very high. What is specific surface area? Specific surface area SSA is equal to area upon volume. Volume is nothing but area into depth. Area by area into depth means 1 by depth or 1 by height. But all the soil particles we assume spherical in shape. So area of a sphere is 4 pi r square and area volume of a sphere is 4/3 pi r cube, inversely proportional to radius. Size, here radius relates size of the particle. Lesser the size of the particle, more the specific surface area of the particle. In the solution sheet, in the solution discussion, I have shown you various particle sizes. Boulder, big boulder greater than 300 mm, cobble 300 mm to 80 mm, gravel 80 mm to 4.75 mm, sand 4.75 to 0.075 mm, next silt 0.075 to 0.002, clay less than 0.002. So lesser the size, clay is having the small size, have more specific surface area. Also the specific surface area finds its application in concrete technology subject also. There we find specific surface of the cement. We express the cement in centimeter square per gram. Note it that concrete technology subject also this term is used, specific surface area. So this is about the fine grained soils. They have specific surface area is very high due to the smaller size of the particle. This point is to be noted in case of fine grained soils. Fine grained soils also exhibit plasticity characters. Coming to the coarse grained soils, they are expressed in terms of gradation. Well graded gravel, poorly graded gravel, well graded sand, like that we will express in terms of gradation. Particle size expressed in terms of gradation. The behavior of coarse grained soils does not change with change in water content. Change in water content does not change the behavior of the, means water content has no influence on the coarse grained soils, but behavior of fine grained soils changes with change in water content. And verbal description of fine grained soils is based on their plasticity characters also. We will describe the fine grained soils in terms of their plasticity character. We will describe the coarse grained soils based on their gradation characters. These are the main differences. So, these are the main differences to be noted in between coarse grained soils and fine grained soils. Coming to the analysis, 75 micron sieve is widely used in the laboratory because this is the smallest size of the sieve that is available in the laboratory. This sieve is going to distinguish between coarse grained soil and fine grained soil. Okay. For the sieve analysis is done for particles above 75 micron. For particles less than 75 micron, which analysis you do? You do in sedimentation analysis. Particle size more than 75 micron, sieve analysis is applicable. Particle size less than 75 micron, you do sedimentation analysis. How you do the sedimentation analysis? Based on the Stokes law. Based on the Stokes law, you do the sedimentation analysis based on Stokes law. Settling velocity. We will study in environmental engineering. Stokes law. Settling velocity Vs g by 18 into specific gravity minus 1 into d square by mu. Velocity is directly proportional to square of the size of the particle. D refers diameter or size of the particle. So, settling velocity is directly proportional to square of the size of the particle. Based on this concept, one numerical question came in GATE 2011. Depending on the size of the particle, how the settling velocity will vary. This is sedimentation analysis. Hydrometer is an instrument used to measure the specific gravity of the soil solids in suspension. That analysis is based on the Stokes law. That wording is important. Hydrometer is a device used to measure the specific gravity of the fluids, of the soil solids, especially in the suspension. Hydrometer, just basic idea is important. More weightage you will give to sieve analysis only. Just understanding of this concept is required, but weightage of examination is based on the sieve analysis only. Mainly this sieve analysis is used for particle size greater than 75 micron. Particle size greater than 75 micron. What we will do in the laboratory? We will take the different sieves. 80 mm sieve, 20 mm sieve, 10 mm sieve, 4.75 mm sieve. Like that, and 75 micron sieve. These are the different sizes of the sieves that are used in the laboratory. So all these are put in the sieve shaker. One sieve shaker is there, and all the sieves. You do what is the retaining? How much portion is retained on 75 micron? We will calculate. If more than 50% of the soil, retained means leftover. If the more than 50% of the soil retained on 75 micron sieve, we call it as gravel. If it is passing, we will call it as sand. So these are the sizes of the sieves that are available in the laboratory. Different sieve analysis we do. And if more than 50% of the soil is retained on the 75 micron sieve, it is gravel. If more than 50% pass through the sieve, then it is called sand. Passing, then it is known as sand. Because the 75 micron sieve is the deciding criteria for coarse grained soil and fine grained soils. So these are the sizes of the sieves that are available, and we do sieve analysis. Okay. Then what happens? We will plot the table. Weight. What is the weight of the particle? In grams you calculate before doing sieve analysis how much this is weighing. What is the weight of the soil sample? You test in the laboratory. So weight is important. Next, cumulative weight. Cumulative weight that is retained. Sieve number also you do in the first table. Sieve number, which sieve it is D10, which diameter sieve, that is also important. Weight, cumulative weight, and percentage weight that is retained. Percentage weight that is retained, and we calculate percentage final. 100 minus this percentage weight retained. That will give you sieve analysis. And you plot a graph. And we will plot a graph between particle size and percentage final. Particle size and percentage final. This graph is known as grain size distribution curve. Grain size distribution curve. grain size distribution curve. This curve is very important. Grain size distribution curve is extremely useful to classify A. Coarse grain soil, B. fine grain soil. Which of the following is true? This grain size distribution curve is extremely useful for classifying coarse grain soils only, because size of coarse grain soil is comparatively more when compared to fine grained soil. Fine grained soils, because of larger specific surface area, they are having extremely small size. Now particle size and percentage final, if you plot a graph, 100 minus, that is percentage, will calculate. One graph will look like this. All the particles are uniformly passing. There is no size of the particles that is missing. This type of soil is called well graded soil. All particles are present, no missing. So that is well graded soil, well graded, all particles, all grades are present here. This vertical line, if it is coming, this is in semi-log graph. Why you are using the semi-log graphs? Because large number of data can be accommodated on the logarithmic scale. X-axis is logarithmic scale, y-axis is normal. Only log is in x-axis. Okay. This is uniformly graded soil. Uniformly graded soil. Poorly graded soil, another one is there. But or gap graded soil, that soil has some gap like this. This hump always occurs in poorly graded soil or gap graded soil. Gap graded soil. In the gap graded soil, there is a hump. In objective question, they will ask, hump is observed in dashed soil. Option A, well graded soil, uniformly graded, poorly graded, gap. Here, uniform gradation or poorly graded, both are same. Gap graded soil, there exist some gaps. Means soil is formed from two different agencies. Grain size distribution also explains that soil is formed from two different agencies. They are meeting at one place. That is why it is called gap graded soil. Hump exists in gap graded soils only. You make a note here. Hump exists in gap graded soil only. Gap graded soils only. Okay. This point you make a note. This is in semi-log graph sheet. This grain size distribution curve is extremely useful to classify coarse grain soils. Also based on this curve, you can say several things. Several things you can say from the grain size distribution curve. This curve is used in soil stabilization. Soil stabilization. Later you will study next semester, next course. Also this is used in drainage filter. Drainage filters to study. What is graded filter? All you will study. For pavement design. For pavement design also this graded well. Also to know about the gradation of soil. Whether the soil is uniformly graded, poorly graded. Also this gradation also influences the shear strength of the soil. Well graded soil have more shear strength, poorly graded soil or uniformly graded soil have less shear strength. This grain size distribution curve is used in soil stabilization, also used to design the drainage filters, for pavement design, also to know about the gradation of the soil, also it describes the shear strength of the soil. That are the uses of this grain size distribution curve. Also from this grain size distribution curve, we can infer lot of things. D30 terms are there, D30, D10, D60. 30% particles are finer than the sieve opening of diameter D. Means there are more than 30% of the particles pass through the diameter D. 30% of the particles are finer than the sieve of diameter D. That is the meaning of D30. 30% of the particles are finer than the sieve of diameter D. But you see in textbooks what they do, 30% of the particles are finer than this size. What is this size represents? The sieve of diameter D. 10% of the particles are finer than the sieve of diameter D. D10. D60 means 60% of the particles are finer than the sieve of the diameter D. That's what it represents. Among these three, D10 represents effective size of the soil. Effective size of the soil. This D10 has excellent drainage characters. D10 has excellent drainage properties. That's why effective size of the slow sand filter in environmental engineering, rapid sand filter, slow sand filter you study. There you study effective size of the filter ranges from one value will be there. What is the effective size of the filter, slow sand filter or rapid sand filter? D10 value will be expressed there. Why? We are using this filters design because D10 is having excellent drainage properties. That is the reason why you are using this D10 property in environmental engineering also. The effective size of the soil represents the drainage characters of the soil. It has excellent drainage properties. In fact, you can say coarse grained soils have well drainage properties, good drainage properties compared to fine grained soils. That's why gravels are used in railway sleeper saws. In the railway stations, ballast is there. All the ballast is nothing but gravel only. When you pour water from the train, what happens? The water will be absorbed by the gravel. There are excellent drainage properties. You will not use fine grained soils in railway engineering. Only coarse grained soils, gravel is used because it has well drainage properties. That is very important. So some terms are there here. This is grain size distribution curve. Okay, coarse grained soils are used for the railway section sleeper saws because they have excellent drainage properties. Next two terms important are exams, frequently asked exams. Coefficient of curvature and coefficient of uniformity. Coefficient of uniformity. Coefficient of uniformity represents all the sizes of the particles denoted by Cu, represents D60 to D10 ratio. This ratio is important. D60 to D10. Coefficient of curvature is also known as coefficient of gradation. Coefficient of gradation, it expresses how much graded soil it is. Cc is equal to D square 30 upon D60 D10. These points are to be noted as it is. There will be no change in them. For well-graded gravel, Cu greater than 4. This is important. For well-graded gravel, Cu greater than 4. And Cc lies between 1 to 3. For well-graded gravel, Cu greater than 4 and Cc coefficient of uniformity lies between 1 and 3. For well-graded sand, Cu greater than 6. Coefficient of uniformity will be greater than 6. For gravel it is greater than 4. And coefficient of curvature lies between 1 and 3. Well-graded silt is not used, only well-graded gravel and sand, because silt comes into the category of fine-grained soils. Already we discussed the behavior of fine-grained soils changes with change in the water content. But change in water content does not influence the behavior of the coarse-grained soil. Each and every point we are discussing is a lot of value in competitive examinations. Okay, behavior of fine-grained soils, we say that it changes depending upon the water content. So take a soil sample. Let us say this is the soil sample. Add water to the soil sample, the behavior of the soil sample changes. In case of fine-grained soils, FGS, point to be noted here. Water content influences largely on the soil mass. How it influences? We will see through the diagram. This is volume. This is water content. Volume and water content. We already told in the beginning that water content largely influences the behavior of the fine-grained soils. The volume of the fine-grained soils keep on changing with change in the water content. So take a dry soil sample, let us say, or let us say take a dry soil sample. Add water to it. Add water to it. Add some more water. Add some more water. Add some more water to the sample. Like that, its water content keep on increasing. First, initially, what we have taken? Take a dry sample. Add water. When volume increases, again add water. Its volume increases. Again increases. Again increases. Again increases. It goes to peak like this. Or this curve can be interpreted in another way. Take a wet soil sample that is having the largest liquid content in it. Water content is maximum here. Take that sample. Dry the sample. Water content decreases. Again dry. Water content decreases. Again dry. Water content decreases. Dry, dry, dry. At one particular stage, even though you decrease in the water content, there will be no change in the volume of the soil. Understood this concept? Here. We are classifying the boundary water contents like this. We are classifying the boundary water contents. Here it is in the liquid state. Take a soil sample, allow it to dry. Its volume keep on reducing. Wet soil sample this is. So the soil sample is in the liquid state. This is in the liquid state or liquid stage. Soil sample is in the liquid state or liquid stage. Allow it to dry. It becomes plastic. Plastic state. Further you keep on drying. Reduce the water content. Drying means reducing the water content. It converts into semi-solid state. Semi-solid state. After dry, it becomes solid state. Increase in water content. This side, if you see, it is depends upon your seeing. Once in IAS examination, one question is asked. I remember. If a soil sample is allowed to reduce gradually, then what is the behavior of the soil? That is nothing but fine-grained soil. This is a liquid state, allowed to dry, it comes to plastic state, then semi-solid state, then solid state. This boundary, where it crosses from liquid state to plastic state, is called liquid limit. It is denoted by WL. This boundary, where the soil reaches from plastic state to semi-solid state, it is called plastic limit, WP. It is denoted. The boundary water content at which the soil converts from semi-solid state to solid state is called shrinkage limit, WS. This liquid limit, plastic limit and shrinkage limit are the boundary water contents of the soil. This liquid limit, plastic limit, shrinkage limit are nothing but the boundary water contents where soil changes itself from one boundary to another boundary. This graph is important for competitive examinations. Okay, this is the way to analyze the graph. Later we will discuss some points after discussing this. Okay, this is the percentage change in the volume. This state is called dry state. So volume corresponding to the dry state is dry volume. Volume corresponding to plastic limit is V suffix P. This volume is VL. So the slope of the curve remains same at every state. There will be no change because it is continuously rising, or you can interpret another way, continuously falling. The slope of the line does not change here. The line goes on increasing. So slope of the line or gradient of the line does not change. Y is equal to mx plus c. Like that it is in this form. So what we interpret here is slope of the line m is equal to y2 minus y1 by x2 minus x1. In the similar manner we can say VL minus VD y2 minus y1 divided by x2 minus x1 WL minus WS is equal to, this is a shrinkage limit, water content, liquid limit, plastic limit, shrinkage limit. Next, VL minus VP y2 minus y1 divided by x2 minus x1 WL minus WP. This is constant and this is equal to delta y by delta x, which is nothing but tan theta, gradient of the or slope of the curve. This is the slope of the curve. So what is liquid limit? It is the boundary water content at which soil changes from liquid state to plastic state. What is plastic limit? Boundary water content at which soil changes from plastic to semi-solid. What is shrinkage limit? From semi-solid to solid state. At this state volume is called a dry volume. The limit is called a shrinkage limit. So you can represent Vs or Vd. Both are same. Volume of the solids it represents, dry solids. So this is about this graph. Next points we will discuss in the next class.